Hello! In this video, we'll learn how to classify text. Detecting patterns is a central part of natural language processing, and we'll try to answer the following questions. How can we identify particular features of language data that are salient for classifying it? How can we construct models of language that can be used to perform language processing tasks automatically? What can we learn about language from these models? Along the way, we'll study some important machine learning techniques, including Nav-Based classifiers, decision trees, and maximum entropy classifiers. Classifiers can help us to understand the linguistic patterns that occur in natural language by allowing us to create explicit models that capture those patterns. Typically, these models are using supervised classification techniques, but it is also possible to build analytically motivated models. Either way, these explicit models serve two important purposes. They help us understand linguistic patterns and can be used to make predictions about new language data. The extent to which explicit models can give us insights into linguistic patterns depend largely on what kind of model is used. Some models, such as decision trees, are relatively transparent and give us direct information about which factors are important in making decisions and about which factors are related to one another. But all explicit models can make predictions about new, unseen language data that was not included in the corpus used to build the model. These predictions can be evaluated to assess the accuracy of the model. Once a model is deemed sufficiently accurate, it can be used to automatically predict information about new language data. These predictive models can be combined into systems that perform many useful language processing tasks, such as document classification, part-of-speech tagging, sentence segmentation, dialogue, act type identification, and determining entailment relations, and many other tasks. Most models that are automatically constructed from a corpus are descriptive models. In other words, they can tell us what features are relevant to a given pattern or constructions, but they cannot necessarily tell us how those features and patterns relate to one another. If our goal is to understand the linguistic patterns, then we can use this information about which features are related as a starting point for further experiments designed to tease apart the relationships between features and patterns. On the other hand, if we're just interested in using the model to make predictions as part of a language processing system, then we can use the model to make predictions about new data without worrying about details of underlying causal relationships. Classification is the task of choosing the correct class label for a given input. In basic classification tasks, each input is considered in isolation from all other inputs, and a set of labels is defined in advance. Some examples of classification tasks are deciding whether an email is spam or not, deciding what the topic of a news article is from a fixed list of topic areas such as sports, technology, and politics, deciding whether a given occurrence of the word bank is used to refer to a river bank, a financial institution, the act of tilting to the side, or the act of depositing something in a financial institution. The basic classification task has a number of interesting variants. For example, in multi-class classification, each instance may be assigned multiple labels. In open-class classification, the set of labels is not defined in advance, and in sequence classification, a list of inputs are jointly classified. A classifier is called supervised if it is built based on training corpora containing the correct label for each input. Some examples of supervised classifiers are decision trees, Nav-Based, or maximum entropy classifier. A decision tree is a simple flowchart that selects labels for input values. This flowchart consists of decision nodes, which check feature values, and leaf nodes, which assign labels. To choose the label for an input value, We begin at the flowchart's initial decision node, known as its root node. This node contains a condition that checks one of the input value's features and selects a branch based on that feature's value. Following the branch that describes our input value, we arrive at a new decision node with a new condition on the input value's features. We continue following the branch selected by each node's condition until we arrive at a leaf node which provides a label for the input value. In this figure, we have a decision tree model for the name-gender task. Note that three diagrams are conventionally drawn upside down, with the root at the top and the leaves at the bottom. Let's check how our decision tree behaves for the name, for example, Kermit. So at the root node, we first check whether the last letter is a vowel. So for Kermit it's T, it is not a vowel, so we branch accordingly. Next, at the next decision node, we check whether the first letter is K, it is, so we branch accordingly, and then we check at the next decision node whether the last letter is T, it is, so we get our class label M for the male's name. So once we have a decision tree, it is straightforward to use it to assign labels to the new input values. What's less straightforward is how we can build a decision tree that models a given training set. But before we look at a learning algorithm for building decision tree, let's consider a simpler task, picking the best decision stamp for a corpus. A decision stamp is a decision tree with a single node that decides how to classify inputs based on a single feature. It contains one leaf for each possible feature value, specifying the class label that should be assigned to inputs whose features have that value. In order to build a decision stamp, we must first decide which feature should be used. The simplest method is to just build a decision stamp for each possible feature and see which one achieves the highest accuracy on a training data. Once we've picked a feature, we can build the decision stamp by assigning a label to each leaf based on the most frequent label for the selected examples in the training set. That is, the examples where the selected feature has that value. Given the algorithm for choosing decision stamps, the algorithm for growing larger decision trees is straightforward. We begin by selecting the overall best decision stamp for the classification task. We then check accuracy of each of the leaves on the training set. Leaves that do not achieve sufficient accuracy are then replaced by new decision stamps trained on the subset of the training corpus that is selected by the path to the leaf. For example, we could grow the decision tree in our example by replacing the leftmost leaf with a new decision stamp trained on the subset of the training set names that do not start with K or end with a vowel or an L. There are several methods for identifying the most informative feature for a decision stamp. One popular alternative called information gain measures how much more organized the input values become when we divide them up using a given feature. To measure how disorganized the original set of input values are, we calculate entropy of the labels, which will be high if the input values have highly varied tables and low if many input values all have the same label. In particular, entropy is defined as the sum of the probability of each label times the log probability of that same label. For example, this figure shows how the entropy of labels in the name-gender prediction task depends on the ratio of male to female names. Note that if most input values have the same label, for example, if P of male is near 0 or near 1, the entropy is low. In particular, labels that have low frequency do not contribute much to the entropy, since P of L is small, and labels with high frequency also do not contribute much to the entropy, since log of P of L is small. On the other hand, if the input values have a wide variety of labels, then there are many labels with a medium frequency, where neither P of L nor log of P of L is small, so the entropy is high. There are many advantages of decision trees. For example, compared to other algorithms, a decision tree requires less effort for data preparation during preprocessing. A decision tree does not require normalization of data. It also does not require scaling of data. Missing values in the data also do not affect the process of building a decision tree to any considerable extent. A decision tree model is very intuitive and easy to explain to technical teams as well as stakeholders. However, there are also some disadvantages. A small change in the data can cause a large change in the structure of the decision tree, causing instability. For a decision tree, sometimes calculation can go far more complex compared to other algorithms. Decision tree often involves higher time to train the model, and decision tree training is relatively expensive as the complexity and time has taken a toll. The decision tree algorithm is inadequate for applying regression and predicting continuous values. Nav-based algorithm is fast and always ready to learn, hence it is best suited for real-time predictions. The probability of multi-classes of any target variable can be predicted. With the help of collaborative filtering, Nav-based can help to build a recommendation system. This system uses data mining and machine learning techniques to filter the information which is not seen before and then predict whether a user would appreciate a given resource or not. Due to its better performance with multi-class problems and its independence rule, it performs better or have a higher success rate in text classification. Therefore, it is used in sentiment analysis and spam filtering. In Nav-based classifiers, every feature gets a say in determining which label should be assigned to a given input value. To choose the label for an input value, the Nav-based classifier begins by calculating the prior probability of each label, which is determined by checking frequency of each label in the training set. The contribution from each feature is then combined with the prior probability to arrive at a likelihood estimate for each label. The label whose likelihood estimate is the highest is then assigned to the input value. In this figure, we can see an abstract illustration of the procedure used by the Nav-based classifier to choose the sentiment for a document. In the training corpus, most documents are neutral, so the classifier starts out at a point closer to the neutral label, but it then considers the effect of each feature. In this example, the input document contains the word love, which is a strong indicator for positive sentiment, and then it also contains the words this movie, which is a weak indicator for neutral sentiment. After every feature has made its contribution, the classifier checks which label it is closest to and assigns that label to the input. In this figure, the following process is illustrated. Individual features make their contribution to the overall decision by voting against labels that don't occur with that feature very often. In particular, the likelihood score for each label is reduced by multiplying it by the probability that an input value with that label would have the feature. For example, if the word cloud occurs in 25% of the neutral documents, 11% of the negative documents and 1% of the positive documents, then the likelihood score for the neutral label will be multiplied by 0.25, the likelihood score for the negative label will be multiplied by 0.11, and the likelihood score for the positive label will be multiplied by 0.01. The overall effect will be to reduce the score of the negative label slightly more than the score of the neutral label, and to significantly reduce the positive label with respect to the other two labels. Nav-based begins by calculating the prior probability of each label, based on how frequently each label occurs in the training data. Every feature then contributes to the likelihood estimates for each label by multiplying it by the probability that input values with that label will have that feature. The resulting likelihood score can be thought of as an estimate of the probability that a randomly selected value from the training set would have both the given label and a set of features, assuming that the feature probabilities are all independent, as shown in this figure here. Nav-Based approach represents a text document as a bag of words, that is an unordered set of words keeping only their frequency in the document. And the classifier works as follows. For a document D, out of all classes C, from the set C, the classifier returns the class C hat, which has the maximum posterior probability given the document. This calculation is obtained by using the Bayes rule. The Bayes rule says that the probability of a class given the document equals the product of the probability of a document given class and probability of a class divided by the probability of a document. So let's formalize what was explained in previous slides. Nav-Based classifier calculates maximum a posteriori, that is, among all classes from a set of classes C, it tries to find the most likely class. The class for which this probability of a class given document has the highest value, the maximum value. Using the Bayes rule, we can replace it with this expression, and from this expression we can notice that denominator does not depend on class, so we can omit it. It will not change our calculation. So we can rewrite the expression like this, and here we have this term P of D given C, probability of a document given class. We call this term the likelihood of the document. And this second term, P of C, probability of class, we call the prior probability of a class. We can then inspect this probability of D given C. And since we represent a document as a set of features, we can replace it with this expression. So the probability of all features in a document given a class, and furthermore, using the independency assumption, that is that the features are mutually independent, we can write the likelihood as a product of individual terms, product of individual features given the class, and by using the notation for the product, we can rewrite the expression for our most likely class with this expression. To apply the Nav-Based classifier to text, we need to consider word positions by simply walking an index through every word position in the document. Nav-based calculations are done in log space to avoid underflow and increase speed. By considering features in log space, the equation computes the predicted class as a linear function of input features. Classifiers that use a linear combination of inputs to make a classification decision are called linear classifiers. How can we learn the probability of a class and probability of a feature given the class? Let's first consider the maximum likelihood estimate. We'll simply use the frequencies in the data. For the document prior, P of C, we ask what percentage of the documents in our training set are in each class C. Let NC be the number of documents in our training data with class C, and N be the total number of documents. Then we can write the following expression for the probability of C. To learn the probability of feature given the class, we'll assume a feature is just the existence of a word in a document's bag of words, and so we'll want P of Wi given C, which we can compute as the fraction of times the word Wi appears among all words in all documents of topic C. We first concatenate all documents with category C into one big category C text. Then we use the frequency of Wi in this concatenated document to give a maximum likelihood estimate of the probability, as shown with this expression here. Here, the vocabulary V consists of the union of all the word types in all classes, not just the words in one class C. A problem with maximum likelihood may appear if we have some new words in our test set that did not appear in the training data set. These zero probabilities cannot be conditioned away, no matter the other evidence. Since Nav-Based naively multiplies all the feature likelihoods together, zero probabilities in the likelihood term for any class will cause the probability of the class to be zero. So the simplest solution is the Laplace add-one smoothing for Nav-Based, as shown here. So we simply just add 1 to each count of words that was 0. And by introducing this 1 into our equation, we get the following expression for calculating probabilities of words given a class. Here we have the pseudocode for the Nav-Based algorithm for training. The function train Nav-Based has two input parameters, set of documents and set of classes, and it returns the log of prior probability of each class, the log of probability of a word given a class, and it also returns a vocabulary which contains all words from our training data set. So to calculate prior probability of a class, for each class C from the C set, we must define the variables ndoc and nc by counting the number of documents in D and the number of documents from D in class C to obtain the log prior for each class. Then we create the vocabulary from the words in all documents, and for each class we create a big doc of C that contains all the documents with class C. Then we want to calculate probability of a word given a class, and to do so, for each word W in our vocabulary, we must count the number of occurrences of a word W in big doc of C in order to calculate the log likelihood. So in the end, we will obtain our goal, which is to find the log prior, the log likelihood, and our set V of words. Now that we have obtained log prior, log likelihood, and the vocabulary V, for a test document, we can call this procedure test Nav-Based with additional parameter of set C, set of classes, and it will return the best C, the best class that it calculates. So the procedure goes as follows. For each class C, we add log prior of a particular class into the variable sum C, and then we go through our test document, and for each position I in test document we take a word. From a test document, and if it is a word from our vocabulary, we update the variable sum of S by adding to it a log likelihood of a word given a class. And in the end, this procedure will return the most likely class, that is the maximum value of all sum of C. Let's go through a worked example. Here we have a training data set with 5 documents, 3 of which are negative and 2 are positive. Our goal is to predict the category label for the test sentence. And to do so, by using the Nav-Based classifier, we first must calculate the prior probabilities of positive and negative categories. So to calculate the probability of negative class, we divide the number of negative documents to the total number of documents, and to calculate the probability of positive class, we divide the number of positive documents with the total number of documents. Then we have to calculate the probability of each word in our test sentence given a class. So for
to calculate the probability of word predictable given the negative class, we must count the number of times a word predictable appeared in negative documents, which is 1, and we must count the total number of words of all negative documents, which is 14 in our example, and these additional values, 1 and 20, go for the Laplace smoothing because the 20 is a total number of words in our vocabulary. In the same manner, we calculate the probability of a word no given a negative class and the probability of a word fun given negative class. A similar calculation is done for the calculation of probabilities of these same words, but for the positive class. So we calculate the probability of a word predictable given the positive class, the probability of the word no given positive class, and the probability of a word fun given the positive class. Now that we have all the probabilities that we need to calculate the probability of category of our test sentence, we can calculate first the product of the prior probability of negative category times the probability of our test sentence given the negative class. So we multiply the prior with these separate probabilities of individual words from our test sentence, and we get this result. And similarly, we calculate the product of prior positive class with the probability of our test sentence given the positive label. So we multiply the prior with individual probabilities of each of these words given the positive class, and we obtain this number. And in the end, we just compared the values that we obtained. So since this one is higher, we can conclude that our naive-Bayes algorithm will predict a negative label for our test sentence.
There are many advantages of naive-Bayes classifier. The algorithm is fast and easy to implement. If the independence assumption holds, then it works more efficiently than other algorithms. It requires less training data, it is highly scalable, it can make probabilistic predictions, it can handle both continuous and discrete data. It is insensitive towards irrelevant features, it can work easily with missing values, it is easy to update on arrival of new data. It is best suited for text classification problems. The major disadvantage of a naive-Bayes algorithm is the strong assumption about the features to be independent, which is hardly true in real-life applications. The problem can also be data scarcity or zero frequency. If the category of any categorical variable is not seen in training dataset, then model assigns zero probability to that category, and then a prediction cannot be made. Therefore, some modifications of the algorithm are necessary to improve it. The maximum entropy classifier uses a model that is very similar to the model employed by the naive-Bayes classifier. But rather than using probabilities to set the model's parameters, it uses search techniques to find a set of parameters that will maximize the performance of the classifier. In particular, it looks for the set of parameters that maximizes the total likelihood of the training corpus, which is defined with the following equation. So probability of features is calculated as the sum over x is in the corpus of conditional probabilities of label of x given features x. And here, the conditional probability of a label given feature is calculated as the ratio of the joint probability of label and features and the sum over labels of the joint probability of label and features. Because of the potentially complex interactions between the effects of the related features, there is no way to directly calculate the model parameters that maximize the likelihood of the training set. Therefore, maximum entropy classifiers choose the model parameters using iterative optimization techniques, which initialize the model's parameters to random values and then repeatedly refine those parameters to bring them closer to the optimal solution. These iterative optimization techniques guarantee that each refinement of the parameters will bring them closer to the optimal values, but do not necessarily provide a means of determining when those optimal values have been reached. Because the parameters of maximum entropy classifiers are selected using iterative optimization techniques, they can take a long time to learn. This is especially true when the size of the training set, the number of features, and the number of labels are all large. The maximum entropy classifier model is a generalization of the model used by the Nav-Based classifier. Like the Nav-Based model, the maximum entropy classifier calculates the likelihood of each label for a given input value by multiplying together the parameters that are applicable for the input value and label. The Nav-Based classifier model defines a parameter for each label, specifying its prior probability, and a parameter for each feature-label pair, specifying the contribution of individual features towards a label's likelihood. In contrast, the maximum entropy classifier model leaves it up to the user to decide what combinations of labels and features should receive their own parameters. In particular, it is possible to use a single parameter to associate a feature with more than one label, or to associate more than one feature with a given label. This will sometimes allow the model to generalize over some of the differences between related labels or features. Each combination of labels and features that receives its own parameter is called a joint feature. Note that joint features are properties of labeled values, whereas simple features are properties of unlabeled values. Typically, the joint features are used to construct maximum entropy models exactly mirror those that are used by the Nav-Based model. In particular, a joint feature is defined for each label corresponding to W of label, and for each combination of simple feature and label corresponding to W of F and label. Given the joint features for a maximum entropy model, the score assigned to a label for a given input is simply the product of the parameters associated with the joint features that apply to that input and label, given with this equation. The intuition that motivates maximum entropy classification is that we should build a model that captures the frequencies of individual joint features without making any unwarranted assumptions. An example will help to illustrate this principle. Suppose we are assigned the task of picking the correct word sense for a given word from a list of 10 possible senses, labeled A to J. At first, we are not told anything more about the word or the senses. There are many probability distributions that we could choose for the 10 senses, such as these given in the table. Although any of these distributions might be correct, we are likely to choose the distribution 1, because without any more information, there is no reason to believe that any word sense is more likely than any other. On the other hand, distributions 2 and 3 reflect assumptions that are not supported by what we know. One way to capture this intuition, the distribution 1 is more fair than the other two, is to invoke the concept of entropy. In the discussion of decision trees, we described entropy as a measure of how disorganized a set of labels was. In particular, if a single label dominates, then entropy is low, but if the labels are more evenly distributed, then entropy is high. In our example, we choose distribution 1 because its label probabilities are evenly distributed. In other words, because its entropy is high. In general, the maximum entropy principle states that among the distributions that are consistent with what we know, we should choose the distribution whose entropy is highest. Next, suppose that we are told that sense A appears 55% of the time. Once again, there are many distributions that are consistent with this new piece of information, such as these given in the table, distributions 4, 5, and 6. But again, we will likely choose the distribution that makes the fewest unwarranted assumptions, in this case distribution 5. Finally, suppose that we are told that the word up appears in the nearby context 10% of the time, and that when it does appear in the context, there is an 80% chance that sense A or C will be used. In this case, we have a harder time coming up with an appropriate distribution by hand. However, we can verify that the distribution shown in this table looks appropriate. In particular, the distribution is consistent with what we know. If we add up the probabilities in column A, we get 55%. If we add up the probabilities of row 1, we get 10%. And if we add up the boxes for senses A and C in the plus-up row, we get 8%, or 80% of the plus-up cases. Furthermore, the remaining probabilities appear to be evenly distributed. Throughout this example, we have restricted ourselves to distributions that are consistent with what we know. Among these, we chose the distribution with the highest entropy. This is exactly what the maximum entropy classifier does as well. In particular, for each joint feature, the maximum entropy model calculates the empirical frequency of that feature. That is the frequency with which it occurs in the training set. It then searches for the distribution which maximizes entropy, while still predicting the correct frequency for each joint feature. An important difference between the naive-based classifier and the maximum entropy classifier concerns the type of questions they can be used to answer. The naive-based classifier is an example of a generative classifier, which builds a model that predicts the joint probability of input and label pair. As a result, generative models can be used to answer the following questions. What is the most likely label for a given input? How likely is a given label for a given input? What is the most likely input value? How likely is a given input value? How likely is a given input value with a given label? What is the most likely label for an input that might have one of two values, but we don't know which? The maximum entropy classifier, on the other hand, is an example of a conditional classifier. Conditional classifiers build models that predict the probability of a label given the input value. Thus, conditional models can be used to answer the questions 1 and 2, however, the conditional models cannot be used to answer the remaining questions 3 to 6. In general, generative models are strictly more powerful than conditional models, since we can calculate the conditional probability from the joint probability, but not vice versa. However, this additional power comes at a price. Because the model is more powerful, it has more free parameters which need to be learned. However, the size of the training set is fixed. Thus, when using a more powerful model, we end up with less data that can be used to train each parameter's value, making it hard to find the best parameter values. As a result, a generative model may not be as good a job at answering questions 1 and 2 as a conditional model, since the conditional model can focus its efforts on those two questions. However, if we do need answers to questions like 3 to 6, then we have no choice but to use a generative model. The difference between a generative model and a conditional model is analogous to the difference between a topographical map and a picture of a skyline. Although the topographical map can be used to answer a wider variety of questions, it is significantly more difficult to generate an accurate topographical map than it is to generate an accurate skyline. In order to evaluate our classifier, we need a robust metric. However, accuracy is not a good metric when the goal is to discover something that is rare or at least not completely balanced in frequency. Therefore, we rather use precision and recall that, unlike accuracy, emphasize true positives, finding the things that we're supposed to be looking for. Precision measures the percentage of the items that the system detected that are in fact positive. So precision is given with the following expression. Recall measures the percentage of items actually present in the input that were correctly identified by the system. So recall is given with this expression here. There are many ways to define a single metric that incorporates aspects of both precision and recall. The simplest of these combinations is the F measure, defined with the following expression. The beta parameter differentially weights the importance of recall and precision, based perhaps on the needs of an application. Values of beta that are higher than 1 favor recall, while the values less than 1 favor precision. When beta equals 1, precision and recall are equally balanced. This is the most frequently used metric and is called F beta equals 1 or just F1. Modeling the linguistic data found in corpora can help us to understand linguistic patterns and can be used to make predictions about new language data. Supervised classifiers use labeled training corpora to build models that predict the label of an input based on specific features of that input. When training a supervised classifier, one should split the corpus into 3 data sets: a training set for building the classifier model, a development test set for helping select and tune the model's features, and a test set for evaluating the final model's performance. When evaluating a supervised classifier, it is important to use fresh data that was not included in the training or development test set. Otherwise, the evaluation results may be unrealistically optimistic. Decision trees are automatically constructed tree-structured flowcharts that are used to assign labels to input values based on their features. Although they are easy to interpret, they're not very good at handling cases where feature values interact in determining the proper label. In Nav-Based classifiers, each feature independently contributes to the decision of which label should be used. This allows feature values to interact, but can be problematic when 2 or more features are highly correlated with one another. Maximum entropy classifiers use a basic model that is similar to the model used by Nav-Based. However, they employ iterative optimization to find the set of feature weights that maximizes the probability of the training set. Most of the models that are automatically constructed from a corpus are descriptive. They let us know which features are relevant to a given pattern or construction, but they don't give us any information about causal relationships between those features and patterns.